Time is not what we think it is. We experience it as a constant, a steady river moving at a fixed rate, the same for every second that has ever passed and every second still to come. We build clocks around this assumption. We build physics around it. We build our entire understanding of cause and effect on the idea that time flows at one consistent speed through the universe, everywhere, always. In 2026, a reanalysis of quasar data confirmed something that should unsettle that assumption completely. Quasars are the brightest persistent objects in the observable universe. Supermassive black holes at the centers of ancient galaxies, blazing with energy detectable across billions of light years. Because they are so distant, we observe them as they existed deep in the past. And because they pulse in precisely measurable patterns, we can treat those patterns as clocks, ancient timekeepers embedded in the early universe, ticking away in a time we can compare to our own. When scientists compared the pulse rates of quasars from the early universe against those from the more recent universe, they found a systematic and consistent difference. The ancient ones ran slow, not because of gravitational time dilation, not because they were near massive objects warping space-time locally, but as a uniform property of the cosmic epoch itself. Time in the early universe moved at a fraction of the rate it moves today. The universe was young, and time was barely crawling. This is not a marginal effect hidden in noise. The 2026 analysis, the most comprehensive quasar timing study ever conducted, covering thousands of objects across multiple cosmic distances, confirmed the pattern cleanly and consistently. The further back you look, the slower time ran. The relationship holds across the data without exception. What it means depends on the theoretical framework you apply. In some models, this slowing is a known consequence of how rapidly space was expanding in the early universe and carries no further implications. But in others, models that have been drawing increasing attention from physicists, time is not a fundamental dimension of reality at all. It is an emergent property, something that arises from the state of the universe, changes as the universe evolves, and has no guarantee of remaining constant or continuing at all. If time was nearly frozen at the moment of the Big Bang and has been accelerating ever since, the question that follows is not comfortable. What is it accelerating toward? And if time can speed up, can it also slow again? Can it stop entirely? Some models say yes. That time, like matter and energy and space itself, is something that emerged from the beginning, something that changes, and something that could, in principle, end. We do not know if this is true. The data confirms the slowing. The interpretation remains open. But we now know that time has not always moved the way it moves today. And that changes what we thought we understood about the word forever.